Black holes, those invisible colossi of space, are true gravitational abysses, capable of swallowing entire stars, planets, and even light itself. They are regions where space and time bend to such an extent that human logic becomes insufficient to describe what happens within. Imagine traveling toward one of them, crossing the boundary known as the event horizon, the point of no return. What would you see? What hidden secrets would unfold before your eyes? This is the journey that leads us to the heart of the Milky Way, where some 26,000 light-years away rests a cosmic monster of unimaginable proportions, a supermassive black hole whose mass equals millions of suns compressed into a single point, casting its colossal shadow across the fabric of the universe. But this giant is not an exception. Research shows that nearly all galaxies harbor supermassive black holes at their cores, true cosmic engines that shape the evolution of the stars around them. The great question is, where did these gravitational beasts come from? How were they born, and what role did they play in building the universe we know today? Observing something that refuses to emit light is a tremendous challenge, but the cosmos itself leaves us clues. In 2008, satellites detected an extraordinarily bright gamma-ray burst, the most energetic light ever recorded, born from a cataclysmic event. This flash traveled billions of light-years before being captured by our telescopes, revealing the signature of an extraordinary phenomenon, the birth of a black hole from the violent death of a star. Stars, those cosmic factories of elements, shine as they burn hydrogen and other nuclear fuels in intense reactions. Yet a moment arrives when this vital energy runs out. When it does, the core collapses under its own weight, and the star may explode in a supernova, scattering its luminous remains across space. But what is left behind is even more fascinating. A core crushed to unimaginable densities, which can transform into a neutron star, or, in more extreme cases, into a black hole. It is at that instant that gravity conquers all known forces, and matter ceases to exist as we understand it, compressed into a region so dense that not even light can escape. The physicist Albert Einstein revolutionized our understanding by showing that gravity is not merely a force of attraction, but the very curvature of space-time itself. Planets orbit stars because they are trapped within this curvature, like balls rolling on a bent surface. Now imagine compressing the mass of an entire star into an infinitely small point. The result is a black hole, a deep tear in the fabric of the universe. The scientist Kip Thorne described this process as the transformation of the energy of matter into the pure energy of distorted space-time. It is this energy that allows a black hole not only to exist, but also to violently influence everything around it, from nearby stars to entire galaxies. But what, after all, happens if someone ventures too close to a black hole? Science fiction loves to play with this idea, but real physics offers darker hints. In stellar mass black holes, the difference in gravity between the front and back of a spacecraft would be so brutal that any object would be stretched and torn apart in a phenomenon known as spaghettification. In supermassive ones, the fall might seem gentler, but it would still inevitably lead to the final destination, the core, where the laws of physics cease to function. Simulations suggest that crossing the event horizon would feel like plunging into a cosmic waterfall, where even space and time themselves flow toward the unknown, dragging everything along. Chat GPT Roterista. Modern studies go even further. Some scientists believe black holes may contain passages to other regions of the universe, or even to entirely different universes through a theoretical structure called a wormhole. This possibility remains pure mathematical speculation, but it reveals how these mysterious entities could be far more than cosmic prisons. Inside them, energy does not dissipate as we know it. Instead, it accumulates until reaching extreme states, such as Planck density, where all of modern physics collapses. It is like attempting to grasp the very instant of the Big Bang, condensed into a single region. And black holes are not merely silent devourers, they can also be creators of cosmic chaos. When matter falls toward them, part of it is expelled in jets of energy so powerful they span thousands of light years, reshaping entire galaxies. Observations from the Chandra telescope, for example, reveal gigantic cavities carved by these eruptions, capable of halting star formation or, paradoxically, seeding heavy elements that can give rise to planets like Earth. This leads us to consider that, despite their destructive reputation, black holes may have played a vital role in creating the very conditions that made life possible. The future of the universe is also deeply tied to them. Billions of years from now, when stars have burned out their fuel and vanished, black holes will remain as the last guardians of the cosmos. The cosmologist Stephen Hawking offered a new perspective when he predicted that, slowly, they will not last forever. Through a process known as Hawking radiation, these mysterious entities can lose energy until they evaporate completely, disappearing in a final burst. If this is true, the universe, in its final breaths, will be populated only by black holes in slow decay, until the very last one fades away, bringing the cosmic story to its ultimate end. On the vast stage of the cosmos, black holes do not act alone. In some cases, they dance in pairs, orbiting each other in a gravitational choreography that can last billions of years. When they finally merge, they release an unimaginable amount of energy in the form of gravitational waves, ripples in the fabric of space-time, that travel across the galaxy like echoes of a cosmic collision. These waves were first detected in 2015 by the LIGO Observatory, confirming one of Einstein's boldest predictions of general relativity. The impact of this discovery was monumental because it not only proved the existence of binary black holes, but also gave us a new way to listen to the universe, as if we had opened a window to hear its deepest heartbeats. Each detection reveals ancient stories, collisions that happened billions of years ago and are only now reaching us. And it doesn't stop there. The universe holds even more astonishing encounters. Imagine what will happen when our galaxy, the Milky Way, collides with its neighbor, Andromeda, in an event predicted to occur about 4 billion years from now. When it happens, billions of stars will be hurled into new orbits, nebulae will mix, and planets may be cast out into interstellar emptiness. At the heart of this titanic fusion, the supermassive black holes of both galaxies will inevitably be drawn toward one another, spiraling inward until they merge into a single colossus. That merger will unleash a burst of gravitational waves so intense it will ripple across the universe, marking the union of two entire cosmic civilizations into a new giant elliptical galaxy. It is the kind of event that reshapes the cosmic landscape and reminds us that nothing in the universe remains static. Not even the monsters we once believed eternal. But perhaps the most enigmatic, black holes are quasars, true cosmic lighthouses visible from unimaginable distances. These objects are powered by supermassive black holes in a state of insatiable hunger, devouring matter at extreme speeds. As gas and dust spiral toward the event horizon, they heat to millions of degrees and emit radiation so powerful it outshines entire galaxies. Some quasars can be seen billions of light years away, acting as markers that allow us to peer into the young universe when the first galaxies were just beginning to form. The light of these objects shows us a distant past, when black holes were already playing crucial roles in the cosmic architecture, shaping the very structures that now hold the immense tapestry of stars above us. Despite all this knowledge, black holes remain one of the greatest challenges for physics. At their core lies the singularity, a point where known equations break down. Here, the laws of gravity and quantum mechanics clash irreconcilably, and scientists are still searching for a theory that can unify these two fundamental pillars. In this uncharted territory, some of the boldest ideas are born. That black holes may serve as gateways to parallel universes, or that their inner structure might store all the information of what they consume, a paradox that continues to puzzle the greatest physicists alive. Solving this mystery is not just an academic pursuit. It could lead us to uncover the deepest rules governing reality itself. And finally, the great question arises: what role will black holes play in the ultimate fate of the universe? As billions of years stretch into trillions, the stars that now light up the sky will eventually fade, leaving behind a cold, dark cosmos. In this scenario, black holes will remain as the last giants, wandering through eternal silence. Eventually, even they will begin to vanish through Hawking radiation, an incredibly slow process that could take nearly infinite timescales. The universe may then end in a sea of scattered particles, where black holes were the last actors to leave the stage. But until that final breath, they will continue as guardians of unfathomable mysteries, reminding us that no matter how far we advance, there is still an abyss of knowledge awaiting us in the heart of cosmic darkness.